Hello, class. All right, so now we're going to talk about degrees of freedom. We're going to go over some concepts that we discussed in your lecture. And your chapter one textbook goes over degrees of freedom for different types of molecules, and specifically monoatomic and diatomic molecules. And so we'll go into this in some detail. And remember, monatomic molecules are those that have just one atom. Hydrogen, nitrogen, carbon, HNC, those are monatomic molecules. They have three translational modes, so they can move. Essentially, all they can do, because they're so simple, is move in the X, Y, or Z directions. Okay? Translation. They can't rotate because they're not connected to anything. They don't have any much there to rotate with. But diatomic molecules are those with two atoms. So that's like your N2H2CO molecules like that. And they have, in addition to your three translational modes, they can rotate in both the X and Z directions, right? So here you go, right? There's potential movement around the Y direction, the vertical axis, but the problem with that is it doesn't contribute to heat capacity calculations, which is what we care about degrees of freedom for, is getting values like the heat capacity or specific heat capacity with constant pressure or respect to constant volume. And there are quantum mechanical reasons for that we won't discuss in this particular lecture. But that's just to let you know that essentially we're dealing mostly with translational and rotational modes for most of these molecules, although there are exceptions that we'll get into in a bit. So now your text talks about heat capacity, right? And that's a very good concept. And the way the textbook does it is with a capital C, right? But there's also something called specific heat capacity, and that's done with a lowercase c. And that's just taking the heat capacity and dividing by the mass, right? So this is why I have this term now, RD. That's just R divided by M. So it's your gas constant, 8.314, divided by the atomic mass or molecular mass of the gas of interest. And that is then gives you the dry gas constant that we'll use a lot actually in planetary atmospheres, taking that with me. But so these are in terms of specific heat capacities, right? Because you're dividing by mass. So that's why this is a little c. And the reason why you have a 3 here is because, again, for monatomic gases, there's only 3 translational modes, right? And then to then get C sub P or little c sub P, you add another R, as the book shows you, another R or RD in this case. So plus 2 over 2, right? So if you take 3 halves plus 2 over 2 RD, you get 5 halves RD. So that's exactly what we're seeing here. And excuse the handwriting isn't the best here. It's hard to do this on the screen, on a vertical screen, but you get my drift, right? So then you add the 2 over 2, you get 5 halves RD, and then you get little c sub p. And this is the formulation for monatomic gases. Now for diatomic gases, we have 5 degrees of freedom. Remember, you've got 3 translational, 2 rotational degrees of freedom. That's 5. And then you add an extra 1, right? And that'll give you the 7, right? That'll give you the 7 halves RD, or 3.5 if you prefer. So again, the diatomic molecules that have 5 degrees of freedom, these are H2O2, N2CO, gases like those that have 2 atoms. But more complex molecules have even more degrees of freedom, and including maybe vibrational modes, as we'll talk about in a second. Now, so the relevant degrees of freedom for heat capacity calculations really depends on the application being considered. And In particular, temperature is a big thing. Um, so the vibrations, vibrational modes that are also degrees of freedom and the electronic transitions and things like that, they only contribute significantly if temperatures are high enough, right? But in typical applications, like for instance, here's this example. Typical applications, atmospheric room temperature, a little bit above or below that, you don't, those vibrational modes don't contribute to heat capacity. And so we can ignore those. So for example, your book has this very good figure of heat capacity, big C sub V. So with respect to constant volume, and it plots the translational, rotational, vibrational. See, it shows where those contribute at what temperatures, right? You have C sub V on the y-axis and temperature on the x-axis in Kelvin. And we can see that at pretty low temperatures, hundreds of K, less than 1,000 or so, it's only the translational and rotational modes that matter, right? For in this case, hydrogen, H2. And similar things for a lot of other gases that it's only the translational and rotational modes that are being activated because we say that vibrational modes freeze out at these lower temperatures, as your text also says, and they don't actually become important beyond about 1,000 Kelvin. Then they start becoming important for something like hydrogen or other gases as well. So this is why in most typical applications, we don't really figure the vibrational modes don't figure into heat capacity calculations. And this is why we use these equations instead for most typical applications. That's not to say the vibrational modes don't matter. They do, depending on if you're going to a really extreme regime, a magma ocean atmosphere, these modes matter, right? But for typical applications, it's just rotational and translational. Well, I just wanted to emphasize that because there are cases in which we do care about vibrational modes, and then these equations that we have here would be incorrect, right? So let's look into that, right? Let's look into this some more. And in fact, here's some examples. There's this very good site, engineeringtoolbox.com, right? And this site has a lot of thermodynamic data, experimental data that's been measured for these conditions for at different temperatures, trying to calculate the specific heat with constant respect to constant pressure for a bunch of gases, right? So for instance, here's a good example of a diatomic gas, N2, nitrogen. That's the that's the largest component of our atmosphere is N2. And we can see, remember, this is a diatomic molecule, so it's got 5 degrees of freedom. So C sub V would have, 5 halves, right? It'd be 5 degrees of freedom. So you'd have 5 in that numerator, right? But you add an extra 2/2 RD and you get 7 RD, 7/2 RD, which is 3.5. And with at 28 grams per mole, you get something like 1,040 joules per kilogram per Kelvin. Now, note that this is the units on engineeringtoolbox.com. It's kilojoules per kilogram per Kelvin. So you have to divide by 1,000 R value to get the equivalent value from engineeringtoolbox.com. You can see it's pretty much bang on. I mean, it's right there. It's very much the same answer. I guess it's not surprising. N2 is it's a symmetric and inert gas. So this works very well. This coincides very well with our expectations of theory for a diatomic molecule. So let's go on now with hydrogen, right? So again, you've got 2 grams per mole, and it's a diatomic molecule. So you have 7 halves times 8.314 over 0.002, and you get something that's like 14.5 kilojoules per kilogram per Kelvin, which is exactly what, or very close to what the Again, this is all like less than 1% error or something, right? Compared to the observations or the experimental data, right? So again, the theory agrees with the measurements very well. And let's look at yet another example, right? So here we go with O2, right? So oxygen is O2, right? And we've got, what do we have here? The same sort of thing. You've got 32 grams per mole for O2. It's also diatomic, and so your specific heat capacity is with constant pressure is 0.91, something like that, right? Kilojoules per kilogram per Kelvin, and that's what the, pretty close to what the experiments get as well. So again, this is pretty good. Again, this is all at typical temperatures. There's greater error as you can see here when you go to a 600K. There's a pretty good amount of error, 9% error. So, right, 10% error as you get to very high temperatures. But for typical temperatures, this is pretty good, right? But then, then the other things at high temperatures, I had mentioned, other modes and whatnot become important. They start to contribute to the heat capacity calculations so that the typical thermodynamics 101 equations that we use that work for room temperature start to break down a little bit, but for room temperature and just above or a little bit below, they work pretty well, right? So again, we talked about monatomic and diatomic molecules, but there's also triatomic molecules, right? So again, you could imagine that means molecules with three atoms, and they could be linear or nonlinear. And for a linear triatomic molecule, the center of mass is at the center of the molecule. So again, in that direction, in this case, the y direction, the vertical direction rotation doesn't really matter. So they can be treated just like diatomic molecules with five modes or two rotational modes, not three. But for the nonlinear triatomic molecules, so if there's some asymmetry somehow, you do get that third rotation in the y direction for a total of three rotational degrees of freedom, or six total. So let's look at an example of a nonlinear triatomic molecule, and that's water, water itself, right? So you would expect for a linear triatomic molecule, it should have like a symmetrical tetrahedral shape, and the bond angle would be 109 degrees. But in reality, water doesn't fit this mold. It exhibits some nonlinearity because of its dipole moment. It's a polar molecule. So the bond angle between the the H atoms on it is 104.5 degrees. It's a bit off from symmetry. There's some slight asymmetry there that causes it to add that then extra rotational mode. So you have three rotational modes for water plus three translational modes for six total. So then when we compare this to the experiments, we want to capture that, right? So again, you've got the six total modes, three translational, three rotational to get C sub V. 6/2 is 3 RD, plus you add another RD, that's 4, because you get 8/2 is 4. And when you do the math with 18 grams per mole, you get something like 1.85 kilojoules per kilogram per Kelvin, and which is pretty, again, bang on with the experiments for room or typical temperatures, which is great, right? That works for typical temperatures. Again, it seems to me to suggest that we understand nonlinear triatomic molecules pretty well. Okay, so now we're going to start where things start to break down and our classical theory is not always so clean, and then where it starts to break up a bit, right? So remember, your text made an interesting comment that CO2, yes, it's a triatomic molecule. That is true. But it also said it was a linear triatomic molecule. And I'm here to tell you that's not quite true. Uh, so if it were linear, yeah, you would then treat it like a diatomic molecule with only 5 degrees of freedom, only 2 rotational modes and 3 translational modes. And you have a nice clean 180-degree angle in this linear triatomic molecule because it's linear. So let's look at this. We just make those assumptions and it has 5 degrees of freedom. So that means C sub V or little c sub V would be 5/2 RD. Then you add the extra bit there to get 7, right? You get 7 over 2 RD, which is 3.5 times 8.314 over 44 grams per mole or 0.044 kilograms per mole. And you get something like 0.66 kilojoules per kilogram per Kelvin, which is not coincident with what we have in the table. So from engineeringtoolbox.com, they get values more like zero point 0.8 or more, 0.9, 0.85, 0.87, depending on the temperature, or less than, or 0.76. So there's a big error, right? This is not within 1% or 2% even of the experiments. Our value is not within that range like the others. It's more like 20, 30 or more percent error. And so why is that, right? It's because CO2 is not really a linear triatomic molecule. It is triatomic, don't get me wrong, but the thermodynamics 101 textbook explanation is wrong. Because the thing is, the idea, yes, and many molecules, vibrational modes don't become important until high temperatures. But for CO2, it actually happens at pretty low temperatures. You start getting some input from the vibrational modes even at lower temperatures, typical temperatures. And so that's going to mess with the heat capacity calculations. And so that will interact with your rotational modes and cause CO2 to become bent and slightly nonlinear. So that's what's happening here. And that's explained also in some papers like this one that I cite here by Jensen et al. 2020. So I would recommend reading that for more information. But in reality, when you're trying to use these heat capacity values, like I care a lot about them in my own climate models, and we don't use these simple room temperature parameterizations, right? We we use our own parameterizations based off of experimental data, and that's what's really done in these models is that to accurately capture using things called the showmate equation, for instance, that is a common parameterization that fits the experimental data that people put in models. And we do things like that to properly capture the behavior of the heat capacities of different gases. So that's what's actually done in reality. But this is hopefully gives you a nice conceptual understanding of how degrees of freedom impact heat capacity. If you have further questions on this topic, I'd be glad to go into more details and we can discuss this via email or just talk to me in class. And I will see you next time.